I want to start today with a bit of a provocation.
Right.
If I took every single word in the English language, wrote them all on little slips of paper, threw them in a massive hat, and just started pulling them out one by one, what happens?
You make a huge mess.
Definitely a mess.
Yeah.
But say I did it for a million years.
Yeah.
Would I eventually get a sentence? Would I accidentally write a Shakespeare sonnet?
Ah, the old infinite monkey theorem. I mean, theoretically, if you have infinite time, then sure.
But practically.
Practically, you're just going to get gibberish, total noise.
Right. Because we all know, intuitively that language isn't random. There are rules.
Hmm?
It usually comes before a noun. Queen doesn't usually follow the refrigerator.
Right.
But here's the question that really kicked off our reading for today.
Yeah.
Is language statistically predictable?
That's a subtle difference, but it's a really important one.
It is. Can we use the same hard math that predicts coin flips or, dice rolls to predict which word comes next in a novel? And that's really the premise of the paper we're diving into. Probability distributions in linguistic analysis.
And I'll admit, when I first saw the title, I braced myself for something, a little dry.
Me too.
But it's actually a really compelling look at the hidden architecture of reading. The central argument is that every time you analyze a text, you are unknowingly running a statistical experiment.
You're comparing what you expect to see, the kind of random baseline, against what is actually there.
Exactly. And the difference between those two, that's where the meaning lives. That's the real mission of this deep dive, figuring out how we measure the weirdness, the non-randomness of language.
And to do that, we have to introduce the two main characters of this story. The paper splits the entire linguistic world into two camps.
The first camp is discrete variables.
These are the counters.
Yep. Things you can count on your fingers, even if you had 1,000,000 fingers. How many times does the word "the" appear in this chapter? It's 5 or it's 6. It's never 5.5.
Got it. And the second character.
Continuous variables. These are things you measure. Time, pitch, intensity.
Like, how long does it take a speaker to say the vowel ah?
Right. It could be 0.5 seconds. It could be 0.5001 seconds. It's a sliding scale.
So counting versus measuring, that's our whole framework. I think we should start with the counting, because the paper uses this metaphor that anyone who's taken like a Stats 101 class will recognize immediately.
The urn model.
The classic vase full of marbles.
It's everywhere for a reason. Imagine an urn filled with marbles, some red, some blue. The urn model of language suggests that writing a sentence is pretty much the same as blindly pulling marbles out of that jar.
Okay, but that implies two very specific, very rigid rules. First, the chance of picking a red marble, let's call that the word "the," that chance never changes.
And second, picking one marble doesn't change what you pick next. Independence.
And that's where the model immediately hits a brick wall, isn't it?
It has to. Language is literally built on dependence. If I pull the marble new, and the context is American cities, there is a massive probability the next marble is
York.
or Jersey or Mexico. But if the urn model were true, picking new wouldn't change the odds of picking York at all.
They'd be totally unrelated.
And the source acknowledges this right away. They know it's a simplification, but, and this is the key insight, even though the urn model is technically wrong, it gives us a perfect baseline. It acts as a kind of control group.
Because if we assume language is random, then we can calculate exactly how much a specific text deviates from that randomness.
Precisely. To prove this, the author set up a really fascinating showdown. They compare a massive general database of English, the CLEX database, which has, 18.6 million words?
Something like that, yeah.
Yeah.
And they pit that against a specific smaller text.
Yeah.
Brown corpus.
Which is a sample of American English from the 1960s, about 1,000,000 words.
So CLEX is the urn. It's
Yeah.
the true probabilities. The brown corpus is the handful of marbles we just scooped out.
And they picked 4 words to test. The president, hair like the rabbit in harpsichord.
That is a very eclectic list.
It covers the whole spectrum of frequency. So they crunched the numbers. Based on the 18 million words in that big database, they calculated how many times these specific words should appear in the brown corpus if it were just a random sample.
Let's go through the results. What about harpsichord?
Very, very low frequency word. The math predicted it should appear about 1 time in the brown corpus.
And the observed reality.
Exactly 1 time.
Okay, so for obscure musical instruments, the urn model is spot on.
I did pretty well there. But then look at hair. Based on general English, they expected to see it about 8 times.
And in the brown corpus?
Just once.
So rabbits are underrepresented in 1960s America.
Apparently so. But The real smoking gun, the one that blows the whole thing up, was the word president.
I think I can guess where this is going.
The general database, the math, it predicted the word president should show up about 133 times. That's your baseline expectation.
But the Brown corpus is from the 60s.
Yeah.
So you've got JFK, LBJ, the Cold War.
Exactly. The observed count wasn't 133, it was 382.
Wow. That's nearly triple.
It completely exploded the model. And this is where the statistics come in to, confirm what our gut is telling us. They use the binomial distribution.
That's coin flip math, right? Success or failure.
Right. In this case, success is, I found the word president. They ran the numbers using a function called dBinum to see what the odds were of getting 382 presidents just by chance.
And I'm guessing the computer just laughed at them.
Pretty much, yeah. The probability was effectively 0. It is statistically impossible for that to happen randomly.
So this proves that the Brown corpus has a personality. It's not just a random scoop of English. It's a specific slice of reality where the word president is almost magnetically attracted to the text.
And linguists call that clumping. Words clump together based on topic, on context. But actually, that clumping creates a bit of a headache for the binomial distribution.
How so?
Well, the binomial formula involves calculating factorials. You're multiplying these massive strings of numbers. When your text has millions of words, so n is huge, and the probability of a word is tiny, so p is small, the math just gets incredibly clunky.
Right, because most words are rare. We're usually not testing for we're testing for harpsichord.
Exactly. So for rare events and large texts, we swap the binomial for something a little more elegant. The Poisson distribution.
Named after Simeon Denis Poisson.
Who, despite the name, had nothing to do with fish.
Oh.
The Poisson distribution it's beautiful. It boils everything down to one single parameter, lambda.
Which is just the rate of occurrence.
Yeah. Instead of asking, did I win the coin toss a million times, we're just asking, on average, how often does this thing happen?
Okay, so to show this, the paper moves away from American politics and takes us to a Dutch novel, Max Havelaar.
A classic. And they tracked the word het.
Which is the Dutch neuter form of the...
Right. They chopped the whole novel into 1,000-word chunks. Then they just counted how often het appeared in each chunk to see if the Poisson model could predict the pattern.
And this is where I think the visualization in the paper is so telling. If the Earn model and Poisson were perfect, the graph of word frequency should be this smooth, symmetrical hill.
A nice, gentle bell curve.
But the Max Havelaar data? It looks like a city skyline. It's just jagged peaks and valleys.
The paper calls it erratic. There are gaps where het barely appears, and then these huge spikes where it's used constantly.
Which goes back to that clumping idea. An author doesn't just sprinkle words evenly like seasoning. If you're writing a big descriptive scene, you might use the 50 times. If you're writing rapid-fire dialogue, maybe you don't use it at all.
And to prove this deviation mathematically, the source uses a tool called a QQ plot.
A quantile plot. I always think of this as a kind of lie detector for data.
That's a great way to frame it.
You draw a straight line. That line is your ideal. It's what the data would look like if it followed the rules of the model perfectly.
And then you plot your actual data points against that line.
And if the model's a good fit, the dots hug the line.
They should. And for Max Havelaar.
The dots just peel away, especially at the ends, in the tails. It shows that real literature just drifts away from mathematical perfection.
I love that image. It's like the math is trying to contain the story in this smooth curve, and the story just refuses. It breaks the line.
And that deviation is the signal. If the data fit the line perfectly, the novel would just be noise. The fact that it breaks the model tells us there's a human intelligence organizing those words.
So we've covered the counters, the discrete variables. We've looked at Earns, binomials, and Poisson. But now we have to cross the border into the other territory.
Continuous distributions.
This is where we stop counting integers and we start measuring physics.
Vowel duration, pitch, all that stuff. And the paper opens this section with the paradox that, I'll be honest, I had to read twice to really get my head around.
The zero probability paradox.
Yeah, it says the probability of a vowel being exactly 0.5 seconds long is 0. Which just sounds insane. It has to be some length.
It is super counterintuitive, but think about it mathematically. We're dealing with real numbers now, which means infinite precision.
Oh, right.
A vowel could be 0.5 seconds, or 0.500000001 seconds, or 0.499999999 seconds.
Okay, I see. Because there are infinite points on that number line, the statistical chance of hitting one specific perfect point is 1 divided by infinity.
Which is 0.
So if the probability of any specific point is 0, how do we measure anything?
We stop looking for points and we start looking for intervals. We calculate the probability that the duration falls between 0.49 and 0.51 seconds. We look at the density of the data in that area.
And the shape that that density usually takes
Yeah,
is the most famous curve in the world.
the normal distribution, the bell curve.
But here's the catch the paper points out. Real data is messy. If you measure vowel lengths in recording, your average might be, say, 300 milliseconds, not 0. Your curve is going to be shifted and stretched all over the place,
So we have to use standardization.
which feels like a universal translator for stats.
That's a great analogy. In R, you use the scale function. You take your messy, real-world data, you subtract the mean from it, and you divide by the standard deviation.
And poof. Suddenly, your specific messy data is resized to fit perfectly onto that standard bell curve.
And once it's on that curve, we can do the really important work, which is looking at the tails.
The tails are the absolute edges of the belt, right?
Yeah.
The extreme high and low values.
Exactly. Usually we're talking about the extreme 5%. If a data point like a vowel duration falls into that tail, we know it's statistically significant. It's an outlier. It's weird.
So if I'm analyzing a speech and I find a vowel that lands way out on that 5% tail, I know something is up. Maybe the speaker is angry or emphasizing a point or even running out of breath.
The distribution gives you the map of normal so you can spot the weird.
Now, the normal distribution is the star of the show, for sure, but the paper actually opens up the toolkit and shows us a few other distributions that linguists need to know. It's like the specialists team.
Right. You can't solve every problem with a normal distribution. Sometimes you need the t-distribution.
I always think of the t-distribution as the normal distribution's cautious little cousin.
That's fair. It looks like a bell curve, but it has thicker tails.
And thicker tails means it expects more surprises.
Exactly. It assigns a higher probability to extreme events. We use this when we have small sample sizes. If you only have 10 recordings of a speaker, you can't be super confident about what is normal. The t-distribution accounts for that uncertainty.
It keeps you humble. It says, hey, don't be too sure. There might be outliers lurking here.
Then you have the f-distribution. This one is all about ratios,
Comparing two things.
specifically comparing variances. Let's say you want to know if men vary their pitch more than women do. You aren't comparing the average pitch, you're comparing the spread. The f-distribution tells you if the difference in that spread is real or just random noise.
And finally, the workhorse of categorical data, the chi-squared distribution.
This is what you use for tables. If you have a grid showing how many times group A said yes versus group B said yes, you use chi-squared to see if the groups are actually behaving differently.
But the paper throws up a massive warning flag here. It says the raw chi-squared score is basically meaningless on its own.
And this brings us to the concept of degrees of freedom.
Which sounds very philosophical, but it's really just about the rules of the game you're playing.
Think of it like this. The paper mentions getting a chi-squared value of 4. Is that a big number?
Well, depends on the game.
Exactly. If you only have 1 degree of freedom, a score of 4 is huge. It's statistically significant. You should be surprised.
That's like scoring 4 goals in a soccer match. That's a career-defining game.
Right. But if you have 10 degrees of freedom, a score of 4 is nothing. It's barely a blip on the radar.
That's like scoring 4 points in a basketball game. You're probably sitting on the bench.
Precisely. You cannot interpret the score without knowing the context, the degrees of freedom.
So, bringing all this together for you listening, we look at urns, coins, curves, tables. Why does a linguist, or really anyone analyzing a text, need this whole arsenal? Why can't we just, read the book?
Because the human brain is an amazing pattern matching machine, but it's often wrong. We see patterns where there are none. We ignore patterns that are right in front of us.
These distributions, they're the reality check.
They define what chance looks like. If you don't know what random noise looks like, you can never tell when an author or a speaker is doing something on purpose.
The paper actually ends with a really fun example that I think nails this point. It brings in Alice in Wonderland.
Even in a world of total nonsense, the math still applies.
They chop the text into 40 different chunks and they just count the appearances of the word Alice.
And it varies wildly. In some chunks, she's there 10 times. In others, only 3. But using the Poisson distribution, you can actually calculate the likelihood of her appearing in the next chapter.
You can predict the narrative flow with math.
But, and this is what I really want to leave everyone with, remember that the prediction is never perfect.
Because of the clumping we talked about.
Right. Every single case study we looked at today, from the Brown corpus to Max Havelaar to Alice, showed that the real data always drift slightly off that ideal mathematical line.
The earn model is always just a little bit wrong.
But I would argue that the error, that gap between the math and the text, that's not a mistake.
What is it then?
That's the story. That's the author making a choice.
So the math is the canvas, but the deviation from the math, that's the art.
I couldn't have said it better myself.
That is a fantastic place to leave it. Next time you're reading, just remember, you aren't just looking at words, you're looking at data points that are refusing to be random. Thanks for diving in with us.
Always a pleasure.